Hi, everyone. Couple of bookkeeping items. I posted a homework set and I focused it almost exclusively on the chapter 5 material, I believe. That was the most recent, so just concentrate on that. I think if you know how to do that well, then you should be in pretty good shape. The chapter 4 stuff, I could have asked you some questions from that, but I think I gave you plenty to work on, and just make sure you understand that. That's working with the continuous distributions. And I sort of have full confidence that if you can do that stuff, then you can do the chapter 4 stuff also. So concentrate on those over the next 5 days or so. I'll post a homework quiz for you to work on next Wednesday, and then that will be due the Friday. That'll be Friday the 10th. Okay, so just be on the lookout for that. I've posted these slides from chapter 6 in Canvas as well, so you should have access to those. And I think that's all I have to say for right now. So let's talk about the normal distribution, okay? This is really probably the most important thing that we'll discuss as it pertains to kind of bridging the gap between all of this probabilistic foundational stuff we've been considering and getting into some statistical applications. So what we're going to talk about is just what the normal distribution is, and how we use it. And in general, you can't, if you really want to make everything completely independent of a particular normal distribution, you have to convert to something called the standard normal distribution. Technically speaking, there are infinitely many possible normal distribution curves. It all depends on the kind of data that you're looking at, the units that are in play, and that's annoying because that means that there are infinitely many possible curves you could be looking at. That's not that big of a deal anymore, honestly, just because we have things like Excel available to us. But it's still a good idea to think about taking a given normal distribution situation and converting it to something called the standard normal, which really just kind of takes all of those normal distributions and puts them in the same place. Okay, so that's helpful. We'll talk about calculating probabilities. We'll talk about something called z-scores, which is basically the result of converting things into the standard normal format. And we'll discuss an empirical rule at the end. So like I said, this is clearly the most important and common distribution that we'll study. It's a bell-shaped thing. In fact, sometimes this is called the bell-shaped curve. So when in doubt, most distributions of continuous data, and even some that are discrete, are well approximated by the normal distribution. Things like grades, IQ scores, SAT scores, ACT scores, lots of things like that are normally distributed. So here's the notation. We write X and we write the tilde, and N for normal, and then we list the mean, mu. Okay, the mu is the mean, and sigma is the standard deviation. Standard deviation. Now you have to be on the lookout because sometimes people will use notation where instead of sigma, they'll put sigma squared, which is the variance. You just kind of have to know which notation is being used. Is that second number the standard deviation, or is it the variance, namely sigma squared? So just be on the lookout for that. The first number is always the mean that's listed in this notation. Ooh, there is a slight typo right there that I can see right away. Clearly, this should be a negative infinity right here. Okay, negative infinity. Okay, It'd be kind of hard for a number to be between infinity and infinity. Okay? Strictly between, yeah. So this f of x, this is the density of the normal distribution. Okay, so it's just, look at all these crazy things going on. Look at that, it's a beautiful formula because you have you have the square root of 2 and pi, and then sigma's down there in the denominator of this thing, and you have e raised to, right, and all of that stuff is in the power e to the minus the quantity x minus mu. That mu is the mean squared divided by 2 sigma squared. Okay, so this thing, when you integrate it between minus infinity and infinity, you end up getting 1, and the shape of this thing is a nice bell-shaped curve, and it's symmetric. You can kind of see why, right? I mean, if you kind of think about the fact that the power right here, you are taking x minus the mean and you're squaring it, and that kind of tells you, right, x is the variable, that tells you this thing's going to have a nice symmetrical shape about x equal to mu. Okay, so nice bell-shaped curve with x equal to mu right in the middle of the thing. And let's go, I'm going to go show you a couple of pictures of this now. All right, this is just a straight Wikipedia search for the normal distribution. You can see these nice bell-shaped curves that you get. The blue, red, and orange curves there all have a mean of 0 right in the middle. And the variance, sigma squared, for the blue curve is quite small, equal to 0.2. That's why it's so spiked up around the mean of 0. And then the red curve has a variance of 1, which is why it's not so spiked up, and it's, you know, a little bit more spread out. Remember, we talked about how the larger variance means it's more spread out. And then the orange curve has a variance of 5, okay, which makes it spread out even more, okay, but still it's kind of symmetric about its mean 0. And then of course that last curve right there it's gone back to a fairly small variance of 0.5, which is why it's spiked up more, more so than the red and orange curve at least, but it's been shifted to the left by 2 units because the mean is -2, which is 2 units below 0, but it's still symmetrical about the mean of -2, okay? This distribution was discovered by a German mathematician by the name of Carl Friedrich Gauss, or C.F. Gauss. He's the one who discovered this function right here that plays the role of the density in this thing. So he is the inventor of the bell-shaped curve. He used it in probability and statistical applications. And he is well known as the inventor of this particular distribution. Oftentimes it's even referred to as the Gaussian distribution after him. In fact, if you look at the old German Deutschmark, 10 Deutschmark denomination, of course, now they have the euro as their currency. So this was pre-euro currency. But you look right here. See right here? So you have a nice bell-shaped curve right there. And this is C.F. Gauss right here. That's his face. It's a pretty cool looking hat he's got going on there. But you see the bell-shaped curve right there in the background. And the formula is right there on the Deutschmark. How awesome is that? Man, that would be the day if our currency had a mathematical equation that awesome on it, but no such luck in the old US of A. Okay. Okay. So in the continuous distributions that we've had so far, we talked about how you can find probabilities by using geometry, known functions for the CDF, the cumulative distribution function. Right? That's we call that capital F of X. That's the probability that capital X is less than little x. You can use probability tables, okay, which are oftentimes in the back of statistics, probability and statistics textbooks. You can find them on the web also. That used to be the only way to do these things. We've been making use of Excel, which is technology, the last option. You could also integrate the density to find probabilities. Okay. Geometry is still an option here, but only in the sense that you can just use symmetry, the symmetry that's kind of intrinsic to the bell-shaped curve. And there's some obvious things about that graph. For instance, like, what's the probability of being below the mean? Well, 50%, 0.5. And that's the same as the probability of being above the mean, okay? Because the thing is symmetrical about the mean, okay? So you can use some geometric facts in that sense, just kind of reflecting probabilities around using symmetry. But for the most part, we're going to have to resort to either using tables or technology, okay? So I said that the standard normal distribution is the thing that we're going to want to convert to most often so that we don't have to rely on the fact that, or we don't have to be so beholden to whatever normal distribution we happen to find ourselves in. That's dependent on units and the mean and everything else. The normal distribution has a mean of 0, kind of like those, a few of those curves on that Wikipedia page. And the standard deviation is 1. So the standard deviation would therefore be the same as the variance, okay? In fact, I think one of the examples over there on that Wikipedia page was exactly that. The variance was 1, which means the standard deviation is 1 because the standard deviation is the square root of the variance. So let's go ahead and assume that we have, and a lot of times there's sort of standard notation for the standard normal random variable. Remember, we always put the mean first and the standard deviation second in this notation. So Z is what we often use for this. So we're going to say Z is a standard normal with mean 0 and standard deviation 1. What is f of Z? Okay, so that's a question that we need to ask. And what about the probability that Z is less than 0? What do you think that is? Okay. And what about the probability that Z is between 0 and 1? Now, I remind you, 0 is the mean, okay? So the first probability, the probability that Z is less than 0 is going to be kind of easy. But the probability that 0 is less than Z is less than 1, we're going to have to think about that a little bit. I'm going to show you a probability table that we can use to compute that. And the probability that Z is less than 1.55, we're going to do that as well. Okay, so let's go do that. Okay, so first of all, how do I find the density? Well, I can go back to the formula for the density right here and just plug in sigma. So remember, what is it? Mu was equal to, remember this should be a negative sign right here. So I knew that mu is equal to 0 and sigma is equal to 1 for Z. Okay, so what would f of Z equal? Okay, if I plug in mu equal to 0, and by the way, x is going to become Z here, and sigma equal to 1, I would get 1 over the square root of 2 pi. Okay, 1 over the square root of 2 pi, and sigma is 1, right? So sigma squared is also 1. So this would be e to the minus Z squared over 2. Okay, so that's what the density would be for the standard normal. So this is the density for the standard normal, Z distributed as normal 0, 1. Okay, so there is that. And what about these other things? Well, the probability that Z is less than 0 is pretty easy because we know that for this thing, what's going on? What's right in the middle? Well, mu is equal to 0. So the probability that Z is less than 0, that's this. It's everything to the left of it, okay? So that's just 50%, right? So that's just going to be 0.5. Now, what about the probability that 0 is less than z is less than 1? Well, let's think about that together a little bit. The probability that 0 is less than z is less than 1, actually, the place where the normal curve goes from concave down to concave up, the inflection point on this, that's exactly at 1, okay? Which, by the way, is equal to sigma here, okay? Okay, so that's what that's equal to. So the probability that z is between 0 and 1 is actually given by the area right here. Okay, so there is this. That is the probability that 0 is less than z is less than 1. But what does it equal to, right? What does that equal to? And for that, and incidentally, this other question right here, the probability that z is less than 1.55, what's that equal to? Okay, how am I going to find that? Well, for that, I'm going to have to actually go look at a table, and I can also do it in Excel. So let's go do that. All right, so here is that linked table that was over there in the slideshow in Excel. And the way that this works is it gives these z values, okay? And it essentially down the left-hand column, it gives you whatever the z value is. And some of these are negative, remember, because the mean is equal to 0. That's right in the middle. And it's what it basically is doing is gives you the first two digits to the, well, it gives you the digits to the tenths position down the left-hand column. And then like these numbers right here give the digits to the hundredths position. And these numbers right here are the probability to the left of that, right? So it gives the area to the left of that z score, okay? So for instance, how much probability is there to the left of negative 3.99? Well, it would be this number right here. Okay, so this number would be the probability that z is less than negative 3.99. Okay, that is a tiny probability. Okay, and what about this number right here, 0.0058? Well, that would be the probability that z is less than what? Negative 3.25. Okay, that's how these tables work. Okay. Essentially, there's a notation for this. You use, like this is like the CDF for the standard normal distribution. So you could write f sub z of negative 3.25 if you want. But incidentally, there's also another notation. It's just the capital Greek letter phi of negative 3.25. That's often used also, okay? Negative 3.25, just because this thing comes up so often, okay? The CDF for the standard normal distribution gets its own special letter, namely phi, okay? So we wanted to compute, if you will recall, we wanted the probability that 0 is less than z is less than 1. Well, isn't that the same thing as the probability that z is less than 1 minus the probability that z is less than 0? Okay, and I can look up both of those in here. Okay, where is the probability that z is less than 1? Okay, where is the probability that z is less than 1? Well, I'm going to have to go all the way down here. Where is it? 1.00. Okay, do you see it? Okay, 1.00 is right here. Okay, so that's going to be 0.84134 minus, do I even need to look up the probability that z is less than 0? You can see it right here. Okay, 0.5, but is that really a surprise to us? Better not be. We already computed that just a couple minutes ago. So this is 0.34134, okay? So that is the probability that 0 is less than z is less than 1. The other one they wanted us to compute was the probability that z is less than 1.55. Well, where could I see that? Well, that's right here. Okay, 1.55 is right there. So this is equal to, 0.93943. 0.93943. Okay. But we could also compute this in Excel. So here in Excel, so we're assuming that z is the standard normal with mean 0 and standard deviation 1. How would I get the probability that z is between 0 and 1? Well, I would go equals normal. Okay, look, here's normal standard dist. So there's normal dist and normal standard dist right here. That's what the S stands for. So I go normal standard distribution. Okay, what's the z value? That's the upper one. Well, it's 1. Do I want it to be cumulative? Yes. Then I need to subtract off. Remember, this is going to take me all the way up to 1. I don't want all of that. I want to get rid of the stuff before 0. I could either subtract 0.5 or I could just use the normal standard distribution again if I forgot that that was 1/2. Okay, so that's going to, I subtract off the stuff up to 0. Okay, and I get exactly what I got from the table over there. What about the probability that z is less than 1.55? Well, this is equal to normal standard distribution, right? There's normal standard distribution. What's my z? Well, 1.55 cumulative. Yeah. I get 0.93949. Okay. So there is that. A couple other examples. So if we have the standard normal again, what's the 95th percentile? Now remember, what does this mean? Okay. So the 95th percentile, that means that I want to find a z value so we want z such that the probability that capital Z is less than z, little z, is equal to 0.95, right? So what the picture looks like here is this. So here's 0 right in the middle. Okay, and I want to find this little z value such that what? That right there is 0.95. Okay, and what's the 5th percentile? Well, let me use a letter other than z. So here I want y. Probability that z is less than y. I want this to be 0.05. Okay, so that looks like this. Yeah. Okay, so that would be, so this would be my y, and that would mean that there was 5% right there. Okay, but do you guys, I mean, look at this. Can't you just see that by symmetry, this y, right? What's the connection between this z and this y right here? Okay, is it clear to you that just by symmetry, what's going to be the case? Whatever I discover that z is, because look, how much percentage is above this little z value? That's 5%. And then just by flipping across, right, this is 0 right in the middle. Just by flipping across by symmetry, you can see that y is equal to the negative of whatever this z value is. Okay? So really, to solve both of these problems, I only need to solve one of them and then use symmetry. Okay, so let's go take care of that. Okay, so I want a little z value such that I get 95% below it. There's a couple of ways you can do that. One of them is to kind of stare at the table and look for look for basically 95% or something close to it. And you can kind of see that that happens essentially right here. You don't have it precisely, but you can see that that happens kind of right there. So that means if I were to go over here, that's like 1.6 and, you know, go up here, 1.64 and 1.65. So it looks like this Z, our little Z that gives us the 95th percentile is about 1.64, between 1.64 and 1.65. Let's say that it's just 1.64. Let's go halfway between. Okay. And then remember what was the deal with our Y? Okay. We wanted a Y such that the probability of Z less than Y was equal to 0.05. That was the 5th percentile. Okay, so this was the 95th percentile, right? We wanted that was the 95th percentile. We wanted the 5th percentile. We know that Y was equal to the negative of Z, which is negative 1.645. Okay. And then this Y right here, that's the 5th percentile. 5th percentile, okay? And incidentally, you could have also gotten at that pretty easily by kind of going backwards. My things move along with us. We would want to find something that was close to 5%, okay? And you see, actually, this thing is circled right here perfectly. So what number is that? I'm betting it's negative 1.645. Is it? Let's see. Yeah, negative 1.645. That's exactly what it is. Okay, so negative 1.645. My circles kind of went along with us right there, but you can see that that number is pretty much right on 0.05. That's good. Let's also go look at Excel. Okay, here we are in Excel. Once again, 95th percentile, how do I get it? That means we want a little z such that the probability that capital Z is less than that is 0.95. So what's Z? Well, what you do is you go equals normal, standard, and what you want to do this time, I know what the probability is. I don't need to know the probability. I know the probability, and I want the number that gives me that probability. So that's what this function inv is. It's like the inverse. Okay, normal, standard, inverse, and it asks me for the probability. That's saying, what's the probability that you want to the left of this? And in this case, that's 0.95. That's we get 1.645, basically, exactly what we had before. And we already know that Y is going to be the negative of Z, but let's go ahead and use Excel to pull this off as well. So equals normal, standard, inverse. What's the probability I want? I want 0.05. Okay, and lo and behold, it's exactly it's exactly the negative of our Z value. So that is comforting. Okay, so why are we spending so much time talking about standard normal? Well, like I said, other normal distributions can be manipulated by converting to the standard normal. Okay? Others normal distributions, I mean, you don't have convenient tables, you would have to have infinitely many of them. Now, thankfully, in Excel, you may have noticed that they actually had it said normal distribution, not normal standard. They actually have all of those built in there, but essentially what they're doing to compute those is they're or under the hood, converting to the standard normal, doing the computation, and then going back to the other one. But we can always convert a normal distribution to a standard normal. How? How can we do it? Well, so if X is distributed as normal with mean mu and standard deviation sigma, what we do is we construct Z this way. Okay, if the mean is mu before, that means, right, if the mean of X was mu, I need to subtract mu, okay, so that the mean is now 0. If the standard deviation was sigma before, I needed to divide by sigma so that the new standard deviation is 1. So this is the relationship between z and x. This is how I can convert any normal random variable to a standard normal. This thing will just be normal with mean 0 and standard deviation 1, okay? These things are unitless, okay? So think about it. If x was in dollars, then the mean is in dollars and so is the standard deviation. Those are both in dollars. So if I take dollars minus dollars, which is, x minus its mean, that's still dollars. But then if I divide by the units of dollars, the dollar units are going to cancel and you get a unitless quantity. Okay, so this basically takes any unit at all, any normal distribution at all, and gets rid of the units. Okay, so it's just a way of standardizing everything, putting everything into the z-score world, the standard normal world. Okay. All right, so that's how we convert from any standard normal to a z-score. So here's kind of what I just said. X is that. Then you can write it the one way or the other. The second, or that middle equation, x equals mu plus sigma z. That's just all I did there was multiply by sigma and add mu. Okay, and this form right here is important. Okay. Because what this says is that z, all z is just the number. I mean, think about it. So here's mu, that's a constant, and I just add sigma times z. So z, in the end, the relationship that's going on here, z is the number of standard deviations above, right, if it's positive, or below, if it's negative, the mean. Okay? So that's all that z is telling you. Because if z is equal to 1, then x is mu plus sigma. That means I am 1 standard deviation above the mean. If z is minus 1, okay? If z is minus 1, that means x is equal to mu minus sigma. And that means that x is 1 standard deviation below the mean. So z is literally telling you the number of standard deviations above or below the mean you actually are. Okay, so that's important. Important thing to keep in mind. Okay, so here's the relationship between x and the standard normal, z. Okay, so if x is distributed as normal, mean mu and standard deviation sigma, then z equal to x minus mu over sigma has that a standard normal distribution. We can write it that other way. That's convenient to see that actually z is telling us the number of standard deviations above or below the mean we are. So assuming that x is distributed as normal with mean 2, okay, so this is, don't forget, this is the mean, and this is the standard deviation, okay? Find the probability that x is less than 2. Well, okay, so this is equal to, so what is the distribution of this thing look like? Well, it's going to be like this. What is right in the middle? Well, 2 is. Okay. So that should be 50%. You know what I'm saying? Should be 50%. But let me just write it this way. Okay. So this is the probability that x minus 2, okay, subtract the mean over sigma, right? So this is the mean over sigma, which is 3, okay, is less than, and I do the same thing to the right-hand side, 2 minus 2 over 3. And incidentally, this right here, that's z, isn't it? So this is the probability that z is less than 0, which we know is 50%, but we sort of knew that ahead of time, but I just wanted to practice converting everything to z-scores. Whatever I do to the one side of the inequality, I have to do to the other, right? So it kind of makes sense, right? And all we did when we converted is we translated this into the z world. So here's the x world. And if you go over to the z world, it looks like this. right? So 0 is right in the middle. We did that, right? So that's the relationship between x and z. You can go back and forth. What about the probability that 2 is less than x is less than, right? The probability that 2 is less than x is less than 3, okay? Well, this is equal to the probability, okay, let's subtract the mean and divide by the standard deviation. So 2 minus 2 over 3 is less than x minus 2 over 3 is less than 3 minus 2 over 3, okay? Which is, what's that? So that's the probability that 0 is less than, right? What is this? The reason we did that is because that's z. And this is less than, okay, 3 minus 2 over 3. That is a third. Okay, that's 1/3. Okay, so we want to compute that in, we'll go and actually do this in Excel. I could use tables, but let's go ahead and do this in Excel. So back in a minute. In Excel, again, so down here, if x is distributed as normal with mean 2 and standard deviation 3, this is what we did. We said, okay, we want the probability that 2 is less than x is less than 3. We subtracted 2 and divided by the standard deviation on everything. And we got that that's the probability that 0, right, because z is equal to x minus mu over sigma. 0 is less than z is less than a third. So we can use the standard normal now. So this is normal, standard distribution. Okay, what's our upper z? Okay, so that's going to be a third and 1. Okay, but that's everything up to a third. I don't want that. I want to subtract off everything before 0, but that we already know what that is. That's 0.5. Okay, so that's going to be 13%. 13%. Okay. By the way, we could have gotten that another way. Could have just said that this is equal to, like I said, normal distribution is built in here to Excel. I don't have to convert things to standard normal necessarily. Okay, normal distribution, what's our x? Well, 3 for the upper one. What's the mean? 2. What's the standard deviation? 3. Cumulative, yes. I want to go minus normal distribution. Okay, what's the x? I need to get rid of the stuff before 2. The mean is 2. Standard deviation is 3. Cumulative, yes. And I get the same exact answer. Okay. We want the 95th percentile. So we want, what do we want? We wanted little x with the probability that x less than little x is equal to 0.95. Okay. So what's that going to be? X equals what? Well, let's go ahead and use the ordinary normal distribution function. Okay, so, or actually, hang on, that's not what I wanted. I want the normal inverse, right? Because I know the probability. What's the probability I want to the left of this little x value? 0.95. What's the mean? 2. What's the standard deviation? 3. And I go like that, okay? 6.93. What's the other way that I could have done this? Well, I could have said, I could have actually changed everything. I could have said, okay, if probability, if the probability that x is less than little x, that's equal to the probability that x minus 2 over 3 is less than what? Little x minus 2 over 3, okay? And what's this? So this is equal to the probability that capital Z is less than little z, okay? And I could have computed things this way, all right? So what is z? Oops, maybe I shouldn't put an equal sign here. So what is little z? Okay. Little z is going to be equal to, if I just converted things to the standard normal. So this would be normal standard. So z equals normal standard inverse, and I want 95% probability. Okay, and I get that. So what I would have here is I would have x minus 2 divided by 3 equals z equals 1.645 basically. So what would that tell you that x is equal to? Well, that would mean that x is equal to, I would take 3 times 1.645. Okay, so it would be 3 times 1.645. Then I would have to add, right? So that's basically the standard deviation times the z value I got. And let me just say, this is 3 times z plus the mean, which is 2, okay, which is equal to 3 times 1.645 plus 2. Okay, and what's that equal to? That equals, let me just type it in, 3 times 1.645 plus 2. I get 6.935, which is exactly what we had up here. Okay, so I could have used the standard normal to kind of pull that off as well. Either way, okay. So I just want you to do whatever is most comfortable for you, unless I ask you to do this in a very specific way. Just remember the way that you go back and forth between z and x, and just be able to do that seamlessly. All right. So again, I just want to reiterate something I've already said. So z is equal to x minus mu over sigma. The z-score, it measures how many standard deviations the value x is above, if positive, or below, if negative, the mean mu. So whatever the z is, that's the number of standard deviations that x is above or below the mean. So it's just used to compare data scaled differently. So sometimes you might even have, like, 2 different eras of baseball or something like that. And it's not really accurate to necessarily compare batting averages 100 years apart. What you should probably do is just compare it against the mean and standard deviations. That way you would have a more accurate representation of whether someone was really miles ahead of the competition during that day. So kind of takes data from different eras, even different data from different scales entirely, where you have dollars in one case and maybe pounds in another case. And it kind of just puts everything in the same pot, gets rid of the units so that you can think about it carefully in that context. Okay. So suppose I have, here's an example. Suppose I have one distribution that's normal with mean 75 and standard deviation 8, and another with mean 80 and standard deviation 5. So, and X is a test score on test 1 and test 2 respectively. What z-score does 90 have for each test? Now, z-score would just tell you that would tell you the number of standard deviations above or below the mean. So what about test number 1? Okay. So for test number 1, what would the deal be? So what score does 90 have? Well, you would go 90 minus 75 over the standard deviation, which is 8. Okay, so you would have 15 over 8, which is 1 7/8. Okay, so that would be almost 2 full standard deviations above the mean. Okay, what about test 2? Okay, let me put that up here. What about test 2? Well, what would happen? You would go 90 minus 80, right? So right, our x is 90. So you go 90 minus the mean over the standard deviation. And what do I get? Well, I get 2. Because that's 10 over 5, which is 2. Okay. So which of those two is more impressive? Being 1 7/8 standard deviations above the mean, or being 2 standard deviations above the mean? Okay, and which test is a 90 higher relative to their means and standard deviation? Well, test number 2 is, because it's 2 full standard deviations above the mean. 2 full standard deviations above the mean as opposed to only 1 7/8. Okay, so that's interesting. Okay. Well, let's see here. Let me get rid of this marking on here. Okay, so here's a couple of facts that I'm going to end with here. Something called Chebyshev's rule says no matter what distribution you're in, normal, whatever, standard deviations in some sense kind of measure how spread out the data is. But it turns out there are some things that are just universally true. Okay, so what is universally true no matter what distribution you're in is that if you go out 2 standard deviations to the left or the right of the mean, you're always going to have at least 75% of the data there. And 3 standard deviations is out from to the left or right of the mean is always going to subsume 89%. And if you go out 4.5 standard deviations, you're going to be at 95%. No matter what crazy distribution you're dealing with, that's always true. But in the case of the normal distribution, it's more specific than that. If you go out only 1 standard deviation to the left or right, you're going to encounter a little bit over 68% of the data. That kind of makes sense. If the mean's right in the middle and you go out 1 standard deviation to that inflection point on the bell-shaped curve on each side, that's where the 1 standard deviation happens. And you're going to have 68% of the data roughly within 1 standard deviation of the mean. So between u minus sigma and u plus sigma, 68%. What about within 2 standard deviations? Go out 2 standard deviations. So down to mu minus 2 sigma, up to mu plus 2 sigma, you're going to have about 95.5% of the data. You go out 3 standard deviations, you're going to have almost everything. Okay, so down to mu minus 3 sigma all the way up to mu plus 3 sigma, you're going to have encountered 99.7% of the data. Okay, so I think that's all I wanted to cover here, and you'll get a little bit of practice with the normal distribution and some homework problems a little bit later on. But the main reason we're doing this is because we're about to start using it in a statistical context. That's all for now.